Section 9.1, Inferences for Regression, Video 1. To start our discussion about inferences, we need to remember that an inference is a claim about a population based on what we've measured for a sample. In Chapter 2, when we reviewed linear regression, we were taking sample values for two quantitative variables, setting up a scatter plot, and using technology to come up with the line of best fit, its equation, which invoked a slope and an intercept, and also a value for the correlation, which measured the amount of linear association between the two quantitative variables. In this section, we're going to define a simple linear model. Model being an equation, linear basically meaning that the graph is a line, but algebraically speaking, linear means the highest power on any variable is 1. Outside of statistics, you could have a quadratic model, which means the highest power is 2, and those things do exist. But for our discussion, we'll stick with linear, again, meaning that the highest power on a variable is 1, the consequence of which is the graph is a line. By simple, though, simple means that we're going to have one explanatory variable. This is what makes it simple. And one response variable. Now, why must we distinguish between something that's simple and something that's not, which we will do in Chapter 10? Well, let's talk about a scatter plot that we could create between hours that you study and your GPA. Now, obviously, the hours that you study should have an impact on your GPA, but is it the only thing that can have an impact on your GPA? No. Maybe the number of hours of classes that you're taking could influence your GPA. The more hours you take, the more stuff you have to study, the less time you have to study for each section. Or maybe the hours that you work, or whether or not you have a job, whether or not you have kids, whether or not you're married. Now, I know that those last two are qualitative variables, but there is a way to take a qualitative variable and trick it out to make it look like a quantitative variable and incorporate it in this discussion. We'll see that when we get to multiple regressions in Chapter 10. But for now, we're going to focus on one explanatory variable and one response variable. Now, when we reviewed linear regression back in Chapter 2, the equations that we had for the regression were for a sample because we didn't get all the values for a population in any of those scatter plots. And the equation that we had was y hat is equal to a plus b x, where x was the explanatory variable and y was the response variable, and the hat meant the average predicted value for y for a given value for x. However, we're going to run into a problem when we move to Chapter 10. In Chapter 10, we are going to pick up multiple explanatory variables. Right now, we just have one. So if we pick up more explanatory variables, what would we call them? What variable can we use after x? Well, we can't use y because it's already being used. Should we go back to a? No, that's here. Should we skip to z? Well, there's a variety of things that we could do. But there's a pretty standard protocol for using a variable multiple times but distinguishing it from other versions of it, and that's to subscript it. So eventually, when we pick up more explanatory variables, they will be called x1, x2, however many we have. Now, what do we call their coefficients? A, B, C, D? What if we have more than 26 explanatory variables? We won't, but theoretically it's possible. So how could we come up with a way to represent all these different coefficients, all these different slopes without running out of letters? Well, the exact same way that we did with the x's, by recycling them. So when we get to Chapter 10 and pick up multiple explanatory variables, we'll just be reusing the letter x over and over, subscripted with 1, 2, 3, however many we need. And following suit, we're going to do the same thing with the slopes. We'll recycle the letter b for the slopes and just subscript it with 1, 2, and 3. And in addition to that, we're also going to rename the intersect. Instead of calling it A, we'll call it B0. which makes perfect sense if you just think about these numbers. 0th number, first number, second number, etc., etc. But we're not in chapter 10 yet, so we're not in multiple regressions, which means we're still in simple regressions, which means we only have one explanatory variable. So starting now, we're going to make the transition from how we generically represent a simple regression. Instead of calling it a plus bx, we're now going to call it b0 plus b1x in anticipation of having more explanatory variables in the future. This b0 is still your intercept, the predicted value of y when x is equal to 0, and this b1 is still a slope, which represents the predicted change in y when the x increases by 1. Later on, we'll have multiple variables, and yes, we'll have multiple slopes. Geez, how are we going to draw that line? We'll worry about that later. But my point is, first off, we're going to start calling a sample regression y hat equals b0 plus b1x. Excuse me. And for some reason that I'm not clear on, the author decided this is a good time to transition to capital letters for the variables. I think I know why they're doing it, but they never really give a good explanation. Now, if you still use lowercase x and lowercase y, it's okay. But to be consistent with the notation in the textbook, I will start using capital X for the explanatory variable and capital Y for the response variable when we don't have something more descriptive. Okay, so this is how we're going to represent a sample regression from this point forward. Now we're going to start looking at this from a population perspective so we can start talking about inferences. From a population perspective, we're still going to use a capital Y and we're still going to use a capital X. But no more hat. Now, what are we going to use for the B0 and the B1? We're going to use one of the traditional gimmicks in statistics where if we use a regular letter to represent something in a sample, such as sample intercept and sample slope, we'll use the Greek equivalent in the population version. So instead of B0, we're going to use the Greek equivalent of the letter B. And if you know anything about the Greek alphabet, you probably know that that's the letter beta. Beta looks like a capital B with a long tail and a little bit of curve to it. So instead of, excuse me, not 0. Instead of B0, we'll say beta 0 for the population intercept. And instead of B1 for the population slope, we'll say beta 1. And one more thing. With the population regression, there is a third term. It is a lowercase epsilon. A lowercase epsilon kind of looks like that. That lowercase epsilon is what's called the error term. The word error here does not mean mistake. The word error here means the difference between what we observed and what we predicted. And what this error term does is it accounts for the deviation. It accounts for the deviation between what we observe and what we predict, comma, based on, we'll say, not quantities, we'll say, what's the word I'm looking for? Based on characteristics and values not accounted for by the explanatory variable. That's a lot of words. Let me read it again to make sure it's what I want to say. The error term accounts for the deviation between what we observe and what we predict. In other words, the residual. based on characteristics and values not accounted for by the explanatory variable. So going back to the GPA and hours studying example, if Y represented your GPA and X represented your hours studying, then we could survey a bunch of people, ask them how many hours per week do you study, what is your GPA, make a scatter plot, come up with an equation. What this error term represents is things we didn't account for. How many hours are you taking? How many kids do you have? How many hours per week do you work at a job? Are you married? Again, I know that's a qualitative variable whose answers are not numbers. Yes, you're married. No, you're not married. But as we'll see in chapter 10, there is a way to take a qualitative variable and codify it so that it's quantitative and therefore incorporate it in a model. So that's all this error term represents. All right, so what we're going to do in this section is we're going to do two things with the slope. Number one, we're going to estimate it based on the slope from the sample regression. Number two, we're going to test whether or not the slope is equal to 0 based on the slope from the sample regression. We're also going to do a test for correlation, which we'll see here in a moment.